Swayam Prabha. Digital India. Educated India.
Lecture 30 of groundwater hydrology. So, in this lecture the topics to be covered radiation, logging method. So, within this radiation logging method, natural gamma logging followed by gamma logging, followed by neutron logging, then we will move on to temperature logging, method, followed by caliper logging method, followed by fluid conductivity, logging method, followed by fluid velocity logging method, and then lastly miscellaneous logging methods. So, these are the topics which are proposed in this lecture, and first we will start with the radiation logging. So, in this radiation logging, so within this we will start with the natural gamma logging, and in this, so this is based on the principle is the emittance of natural gamma rays by all rock soil formations. So, that is the principle on which this logging is based on, and here, so this radiation originates from unstable isotopes of potassium, uranium and thorium, and so the natural gamma activity, gamma ray activity of clay is much higher. Much higher than sands and carbonate rocks. So, the application of this of natural gamma logging applications are one in one major application is lithology identification, and of course, there are other this one also, the identification of other fine grained formations. Like clay, shale, etc. So, these are the application, and in this a typical natural gamma ray log will have say depth along the vertical axis, and then the radioactivity along the horizontal axis, and here, so in this case, so this will constitute something like this, and here, so this is 0 0, and this corresponds to, so in the geological log, so maybe this corresponds to sand, again, so here it is sand and gravel, and this is till, so here this is clay, then sandy clay, then again here this is sand and gravel, and then again this is till, and again say this could be gravel. So, like this, so we can identify the formation of the rock using this natural gamma logging. Next, we will go to that is gamma logging. So, here gamma ray radiation originating from, or say coming out from, a source probe. and recorded after its back scatter. Is the gamma log. And so the source probe consists of cobalt 60, cesium 137. So this is generally, so these isotopes of cobalt and cesium. So this is shielded from sodium iodide detector built inside into the probe. So this again the applications of this. So one is lithology identification, then estimation of bulk density and porosity of formations. So if this porosity is denoted as alpha, then this alpha can be written as gamma G minus gamma B. I am sorry, rho G minus rho B divided by rho G minus rho F. So here this rho G is the grain density and rho B is the bulk density. So this bulk density, so this is measured from a calibrated log. And then this rho F, so this is the fluid density. So if so these three parameters are known, so then we can estimate the porosity of formation using this gamma ray logging. And one last application of the third application of gamma ray logging is in location of casing, collars, grouts and zones of hole enlargement. So using this gamma ray gamma radiation. So these casings, collars, grouts and hole enlargement zones can be located. So next we will go to the another, that is the last variety of this radiation logging. So, that is neutron logging. In this case, so this is a neutron source and detector in a single probe. Which produces a record of hydrogen content. Of a borehole. So, here, so this hydrogen content, so this H content is proportional to interstitial water. And therefore, this neutron log measures soil moisture above water table and porosity below water table. So, these two can be measured. So, here what happens is, see, the mechanism is neutrons have same mass as hydrogen, and no charge, no electrical charge. They are neutral. So, when neutrons collide with when neutrons collide with this hydrogen, so there will be energy loss and neutrons are slowed and slowing down of neutrons. So, here this neutron probes use which are currently available use beryllium combined with, so this is beryllium combined with radium 226 plutonium. So, this is plutonium 239 or americium. So, this is 241. So, these isotopes, and this case so obviously, so the application major application is soil moisture estimation. Then followed by porosity estimation. So, obviously, this soil moisture estimation we have seen. So, this is above water table, and porosity estimation, this is below water table. And here, so this for porosity estimation, large holes are used. Large diameter holes are holes, and larger probes are required. And so, here there is one a typical neutron log. So, here this is the depth in meters below ground level, and this is the moisture content in percentage. So, this is neutron log of a shallow well. In an unconsolidated alluvium. So, this is taken from the US Geological Survey, and here, so so based on this, we can say if the moisture content is more, so then we can say it indicates a clay, this one, and here it indicates unsaturated zone, and so here this is sand and sandy silt. Again, for a small depth it is clay, then followed by, so this is sand. So, like this, using the neutron log, we can estimate the soil moisture, and also we can estimate the porosity. Next, we will go to caliper logging. So, in this caliper logging, it is the log of the borehole diameter with its depth. So, this is the And here, so obviously, so this is taken as the average borehole diameter, because at a particular location there can be the borehole may have varying diameters, it may not be perfect circle, and in this case, so the applications are of this caliper logging are lithology identification, and next is the stratigraphy correlation, stratigraphic correlation. So, they can also be used for location of fractures and other openings in rocks. So, let us consider a typical caliper log. So, in this case, so this is the average hole diameter in centimeter along this one, and here there is a depth. So, this is the depth in meters, and in this case, so it may show something like this. So, here this represents a casing, this represents crevices, this represents soft water and sand, and again, so this represents caving shales, again crevices, and this represents liner, and so on. So, in this case, so this is a caliper log, and in this case, so a typical, so this is the caliper, and then so this caliper, so this goes on. So, this is a typical caliper, and here you can show this is the so this is the borehole and with different rock formations. So, this is a caliper. So, this is caliper logging. So, next we will go on to this fluid conductivity logging. So, this is a continuous log of electrical conductivity of fluid in a borehole. So, this is a fluid conductivity So, the probe measures the alternating current voltage drop across two closely spaced electrodes. It is governed by fluid electrical resistivity between the electrodes. And we know that the fluid resistivity, so this if we abbreviate the electrical resistivity as ER, so this fluid electrical resistivity, which is measured in ohm meter. So, this is the reciprocal of, that is the fluid conductivity. And this conductivity is measured in so this is the microsiemens per centimeter. So, this is a microsiemen per centimeter. So, this electrical resistivity is the reciprocal of this one, and the applications so the applications are, one is the location of saline water zone, two is extrapolation. This fluid the conductivity log can be used for extrapolation of water sample data. And in this case, say for example, a typical fluid conductivity log, it will have so this is the depth in meters and then the specific conductance in microsiemen per centimeter. In this case, so suppose this fluid conductivity log, so it has a shape something like this. So, this indicates, so here obviously, so this is a, so this is fresh water overlying a saline water. So, obviously, saline water is a good conductor of electricity. So, its specific conductivity is much higher. So, of the order of say something like 40,000, whereas, so the fresh water has very negligible this one, maybe even less than 1,000 or around 1,000 micro Siemens per this one per centimeter. So, next we will go to the fluid velocity logging. So, in this fluid velocity logging, so it consists of fluid movement tracking or measurement within a borehole. So, its applications to reveal strata contributing water to a well to estimate the hydraulic differences So, estimate differences in hydraulic parameters of various aquifers intersected by a well and thirdly to estimate casing leakages, the leakages in the casing pipes. And in this case, say suppose, so this is a well and it has, so there is a, so this is a well screen, so this is a well screen, this is also a well screen, and here say suppose there is a, so this is a pump. In this case the fluid, so the fluid velocity logging, it will be something like this. I am sorry, it starts at the pump level and so it is so this is the upper aquifer and here this is again and so on. So, basically So, this is a typical so, this is this indicates upper aquifer. So, this indicates and this indicates lower confined aquifer, and so this is the velocity. So, this is the depth. So, this is regarding the fluid velocity logging, and with this, so these three applications, that is the strata revelation, then estimation of differences in hydraulic parameters, and then the casing leakages can be estimated. So, next we will go to the last item of this module, that is on miscellaneous methods of logging. So, in this there are this TV or say television logging, there is acoustic logging, and the third one is the casing logging. So, these are the three important techniques which are grouped under the miscellaneous logging, and here. So, this is now let us come to this TV logging. So, this is in this a TV camera, television camera is a very convenient tool. So, this TV camera lowered in a well. So, it is a wide angle camera. So, this is typically less than say 7 centimeter in diameter, and when it is lowered inside a well, so it provides visual inspection of a borehole. So, the applications are, one is location of changes, geological strata changes, so inspection of well casing condition, then The third one is checking for debris in wells and location of sand entrance zones So, there is also what is called a photo log. So, this photo log, so it is basically photographs taken in a well, that is within a well, at close time intervals. So, this is regarding the TB logging. Next, we will go to what is called the acoustic logging, and this is also known as sonic logging. So, in this so it measures sound velocity through rock surroundings surrounding an uncased fluid filled hole. And so, therefore, if porosity is greater, is higher, the closer is the measured sound velocity, to that of fluid. So, the applications of this acoustic logging are estimation of depth and thickness of porous zones. Second is the estimation of porosity, and third is identification of fractured zones, and next application is the determination of bonding of cement between casing and formation. Casing and the formation, between the casing and the formation. So, these are some of the applications of acoustic logging, and lastly, we will go to this casing logging. So, this casing logging, so here a casing collar locator is used for locating collars, perforations, and screens in casings. And so, it consists of magnets wrapped in a wire coil. So, this fluctuations, voltage fluctuations caused by mass metal, cutting magnetic lines of force, magnetic flux lines are recorded. So, there are other subsurface methods which include the pumping test, the groundwater level measurements, water quality measurements. So, all this have been already discussed, most of this have been discussed in the previous lectures and few might be discussed in the next lectures. So, basically this subsurface investigation of groundwater, it is the more complete and it provides it's almost complete information as compared to the surface information, as compared to the surface investigation. So, that needs to be properly utilized to arrive at the groundwater, to arrive at a holistic investigation of a groundwater. Thank you.